So as far as the rules that we're talking about, the rules are going to apply to Central Valley counties, north up to San Joaquin, south down to parts of Kern County. These rule changes that we're talking about are going to be applying to boilers, steam generators, and process heaters units that are greater than 5 million BTUs. With that, approximately 1,273 units are going to be affected. And the first deadline for these rules is something that we're going to be talking about, a number of times through all these presentations. It's May 1st, 2022. Compliance to both these rules is going to be required for both rules 4306 and 4320. And so we'll go, we've got a team of people that'll be able to help navigate through those rules. So for what we want to go over, a little review over the NOx formation, the two NOx reduction strategies that we touched on previously, and then we'll get into more specifics on our SCR applications and the various ammonia sources that we can work with. And then at the end, we'll have a question and answer if there's anything anybody wants to go over. So boilers and burners that use combustion to make heat are going to have products of combustion, primarily NOx. NOx is going to be a contributing factor to ozone depletion, particulate matter, and acid rain. The three main sources of NOx formation during the combustion process is going to be thermal NOx, where we're going to be creating NOx in high heat locations, prompt NOx, where we're creating NOx in fuel-rich locations within the flame, and then fuel-bound NOx, where our fuel in and itself carries additional nitrogen to promote the production of NOx. So for what we're looking at, thermal NOx is the largest contributor to the overall NOx you're going to see. For ideal combustion, we're taking fuel, mixing free oxygen, free nitrogen that's in the air, and creating CO2, H2O, free nitrogen, and free oxygen, and the resulting is the heat that we use to heat our process. Under high temperatures, free nitrogen and oxygen with that heat create NOx. And as we can see here in the chart, as we increase flame temperature, our NOx production is exponential. So the whole idea is on a lot of our burner technology is to keep that temperature down. So the two strategies that we have, one is burner modifications or new burner. With this technology, we're able to get down to 5 ppm. Typically less expensive than exhaust treatments like SCR. So for units that are smaller than 20 million BTUs, it makes a lot more sense to go with a burner modification or retrofit. One of the downsides to burners, burner technology only, is that to get there, we have to increase air, which decreases our efficiencies. The second option that we have is an exhaust treatment on the back end, which is our SCR. Our NOx reductions can get down to 2.5 ppm. To date, we've got them down on the smallest unit of 8 million BTUs due to special fuels that they're firing. Typically on the SCRs, you're going to have more of an initial cost and continued maintenance than you would have on a burner option. But one of the benefits to an SCR is that you're going to have less impact on efficiency. SCR can be applied to most boilers, steam generators, and process heaters. It's been used for a long time. We've got a history going back to 2006, and it's a proven technology. With SCR, we can meet air district regulations down to 2.5 ppm using an existing 30 ppm burner. And we can also achieve the lowest required ammonia slip of 5 ppm. There are different areas that may require 10 or 5, but 5 is the lowest that you'll see. So SCR also allows for more efficient operation versus ultra low NOx burners. And reasons for that is we're able to reduce the fan horsepower on the FD fan, roughly 30%. It varies by application. in general, we can achieve a lower burner turn down for better load matching and reduce cycling. We're also able to reduce FGR rates since we don't have to have the ultra low NOx FGR rates. Same thing with the XSRs, we're reducing the amount of that needed for operation. And in general, it can raise your fuel to steam efficiency about 0.5% to 1%, depending on what your existing conditions are. So the NOx removal process is a selective catalytic reduction of nitrogen oxide. We're going to convert NOx that's in the combustion flue gas into harmless nitrogen and water without forming any secondary pollutants. Ammonia is what's used to help make this process happen. It's mixed thoroughly with the flue gas by means of an injection grid, and it could be with or without static mixers to get that kind of even distribution to the catalyst face. So down below is just a little illustration of how that operates, where we'd be looking at NOx and O2 passing into our ammonia injection grid. There we would have our mixing hitting the catalyst, and on the outlet, we would be looking at water, nitrogen, and oxygen. For our catalyst, they're made of several precious metals: titanium, rhodium, vanadium, molybdenum, and there's various technologies out there. The ideal catalyst for use in your system would be durable, have a low pressure drop, and have a large surface area. So the ammonia is going to be coated within that surface area, and that's where that liquid barrier there is what would allow it to let this reaction happen with the catalyst. So for the catalyst we use, Umicore is a market leader and the primary source for our catalyst. It's something that's typically in stock, so in a pinch, it's something that we can get readily available. It's a corrugated design, and it's strong with low pressure drop, and it's very compact, meaning that it's got a high surface area per unit of volume. We can design these for vertical or horizontal installations and have them installed as individual cassettes, or for some of the larger assemblies for horizontal flow, we can get them prefabricated and dropped in to help ease the installation process. In general, these catalysts are available on flue gas exit temperatures of 350 degrees to 800 degrees. Now, if your operation is outside of that range, there are means to be able to augment the flue gas temperatures to get it down into the range that we need. So there's options there still. For ammonia injection, it's very important to provide uniform distribution of ammonia in the gas stream to make sure that all of the catalyst is utilized. So ways that we do that is either with single point injection. Single point injection is ideal for round ducts where we have enough length to be able to get the mixing that we need before we get into the catalyst face. What makes this convenient is there's no balancing needed. We'd be able to get everything justified through flow modeling. Or for larger profiles or square ducts, we would look at multi-zone injection, where we would have several lances, each of them with their own balancing valve to be able to balance things out when it gets down to the catalyst face. These are sometimes used with and without static mixers as well. Here's an illustration of a typical SCR installation on an IWT boiler. So you can see here on the left, we've got the boiler. We've got up next on the stack outlet, we've got our injection lances with individual balancing valves. As we make our way down, we've got the SCR housing, and in this particular application, they've got an economizer. So any economizers would be located after ammonia injection in the SCR catalyst. So as far as ammonia sources to make these reactions happen, one of the more common ones is going to be anhydrous ammonia. As you can see here on the NFPA hazard chart, we're going to go through the hazards as they're seen. For health hazards, this comes in as a 3, which is short exposure could cause serious, temporary, or residual injury, even though prompt medical attention was given. For flammability, this is a 1, saying that it must be preheated before ignition can occur. And for instability, it's 0. It's normally stable, even under fire exposure conditions, and are not reactive with water. For anhydrous ammonia, our preferred grade is 4, which is considered refrigerant grade. That would be 99.995% pure ammonia with a 33 ppm limit on water. The OSHA permissible limit for anhydrous ammonia is 25 ppm. This is in California. And the immediate dangerous to life and health is at 300 ppm. For storage of ammonia, typically we're providing these in smaller 150-pound cylinders. Most limits at sites are 500 pounds, so we were able to accomplish that with 3 units. One of the problems with that is as you're changing out tanks, personnel need to get involved and make sure things are flushed and safe to be working on. One of the benefits to bulk tanks is your ammonia provider can connect to it, and they're the ones that are loading in the ammonia rather than your own personnel. But ultimately, the amount of ammonia that you're going to be using is what determines what kind of storage you're going to need. So for anhydrous ammonia, we do have some safety features that we include, like ambient ammonia leak detectors, relief valve discharge lines and pressure switches, airtight ammonia cylinders with cabinets and purge fans to minimize any exposure that you could have, alarm horns and beacons, water capture tanks for vents and relief valves. Another common reacting agent is aqueous ammonia. So it's our ammonia, but in a liquid form. For this, the hazard rating is very similar, but we come down a little bit on the health, down to 2. So we're looking at intense or continued exposure could cause temporary incapacitation or possible residual injury unless prompt medical attention is given. For flammability, we're still the same, where it needs to be preheated before ignition. And stability is the same at 0, normally stable. Aqueous ammonia is a solution of water and ammonia. With it comes lower risk and regulatory issues than if you're dealing with pure ammonia and hydrous ammonia. This solution is a strong base at a pH of above 11. For aqueous ammonia, it is safer and easier to handle and easier to contain leaks than anhydrous ammonia. Typical tank size could be anywhere from 2,000 to 10,000 gallons, but it's ultimately based on your demand. Some of the safety features that we have on aqueous ammonia systems are ammonia leak detectors, alarm horn and beacons. Bulk filled tanks can be filled by the aqueous ammonia supplier, so that keeps your personnel away from it. And the storage tends to incorporate secondary containment in case there is a leak. The next common reagent that we work with is urea. Now, as you can see here, the health hazard on this one has come down along with the flammability. The health hazard is a 1, which means exposure could cause irritation, but only minor. Residual injury, even if no treatment is given. For flammability, we're at a 0. The material will not burn. And for instability, we're also at 0, normally stable, even under exposure conditions. So urea is classified as a non-hazardous ammonia. Ammonia is not present until the solution is treated and converted to ammonia on demand. So this reagent is similar to what's used on a lot of diesel trucks, as commonly known as DEF, diesel exhaust fluid. and typically will come in purity of 32.5% with 67.5% deionized water. That's the most common, but there are various different levels of concentration. For the storage tanks, we're able to do these with plastic tanks, anywhere from 500 to 6,500 gallons. They could go bigger if you need to. And one of the things to be cognizant of when we're looking at the selection for urea and the location is the temperature that'll be in the surrounding area. For lower temperatures, there's a potential for salting out. Solids will precipitate out of the concentration, so we take care to either insulate or provide heaters to make sure that temperatures don't drop based on the concentration that you're using. So the higher concentration, the higher that salt out temperature is going to be. Now for direct injection of urea or aqueous ammonia into the flue gas stream is something that we're able to do. It simplifies the use of urea by eliminating the external conversion of urea to ammonia. It could require multiple injection points to optimize the urea consumption. And in doing this, it also lowers your electrical consumption because you're not using electrical heaters to preheat any air to get either the vaporization of aqueous ammonia or the conversion of urea to ammonia. And with our injectors, we're using constant flow nozzles with DI water and urea added on demand. Now for direct urea injection, RF McDonald does hold a patent for this technology on boiler applications. And that's something that our team can review with you further if you want to look, if this is something of interest. For reagent distribution, liquid or gas injection is going to be controlled by PLC-based controls. Liquid systems include the pump and injection control, and these systems can be integrated into existing systems to allow for remote monitoring. All of our SCR systems can operate with standalone PLC-based controls, so we can work with what you've got there and just work on our own. If control upgrades are desired on your existing equipment, this control can be designed to include advanced parallel positioning or multi-element control with the SCR control integrated in to minimize your hardware and have any additional maintenance. For installations, we have several dating back to 2006, many in the food and beverage, but spanning across many different industries, hospital, oil and gas, universities, pulp and paper. So we've got a lot of experience in putting together systems for just about any application out there. With this list of projects that we have done, we've got many more in design for supply in 2022. So for a summary, the selection of the appropriate emissions control system requires a detailed evaluation of environmental, technical, safety, and economic factors. Contact your local RFM representative to help guide you through this process to determine what makes the best sense for your conditions. Now, given that SCR solutions are more efficient in comparison to ultra low NOx burners, there could still be efficiency improvements available to lower your utility costs if the equipment does not currently exist in your plant. Some of the equipment would be single-stage economizers, two-stage economizers, blow-down heat recovery, and VFD-controlled blower motors. Depending on your current conditions, efficiency gains can be anywhere from 1 to 5%. But it's something that we'd really need to take a look at, and we can calc out what that return on investment would be. So in general, when we're taking a look at the different options that you have, we realize every customer is different. We can help evaluate site-specific conditions and propose customized options to what it is you need. Our evaluations are going to be looking at costs for energy consumption, operations, as well as considerations for 4320 fee compliance. And we can give competitive analysis to make sure that you're making the most of your investment. Now, for the timeline for the rule changes that are going to be occurring, one of the first milestones that we've been talking about is May 1st, 2022. This date, 4306 non-deferred units and 4320, everyone needs to submit an emissions control plan or authority to construct to the district. On December 31st, 2023, 4306 non-deferred units and 4320 users need to come into compliance. January 1st, 2025, this is the start for when invoices will be issued for users paying the fee of 4320, and it'll be issued for operations in 2024. May 1st, 2028 is when 4306 deferred units have to submit their emissions control plan and authority to construct to the district. And ultimately, December 31st, 2029 is when all 4306 deferred units would need to come into compliance. So in conclusion, when navigating the new rules, each user is going to have options to evaluate and see what makes best sense for them. Some early adopters will have the ability to defer compliance until December 31st, 2029. But regardless of the course of action, all users must have compliance plans submitted to the district by May 1st, 2022.